Hi, it's time for another math easy solution. Today I'm gonna go over some math for a change. Yes, if you've been following along, I've been spending most of this year working on my anti-gravity part 6 video, and you can see it there, and also check out that part 6, which I go over MES duality, which is a breakthrough concept for me at least. Pretty bombshell stuff. Anyways, let's go. In this video, I'm going to go over laboratory project logistic sequences. So let's go and cover this. So again, throughout my videos, I've been following along my calculus book, and now I'm going to get to this part. And also, I want to make a note: if the video volume is too low at any part of the video, or in this video or any other videos, I recommend downloading this browser extension recommendation right here, mes.fm/volume-extension, and you can just increase or even decrease the volume of any video on the internet. This is using Google Chrome. It's pretty amazing stuff. Yes, and to go along with the faster playback speed. Anyways, let's go further. So laboratory projects. So recall from my earlier videos in which I would go over very interesting math applications in the form of, quote, laboratory projects, which are included in the end of some sections in my calculus book, which is the Early Transcendentals by James Stewart. So recall the logistic sequences, or actually in this case I'm going to go over logistic sequences or introduce it. So a sequence that arises in ecology, or study of organisms and their environment, is defined by the logistic difference equation, P of n plus 1 equals to K times Pn times 1 minus Pn. Yeah, where Pn measures the size of the population of the nth generation of a single species. So the population would change based on this sequence over here, this formula. Okay, I assume it would be a constant, or it's usually a constant. So let's go further. So notice that the form of this equation is similar to the logistic differential equation for my from my earlier video. Yeah, so compare this with the logistic differential equation as opposed to this one, just a logistic sequence. So here is a link to the notes, but also just put a screenshot from the Stewart calculus book. So the logistic model, as we discussed in sections 9.1, a population often increases exponentially in its early stages, but levels off eventually and approaches its carrying capacity because of limited resources. If P of t is the size of the population at time t, we assume that the rate change right here, dp over dt of the population with time, is proportional to k times p if p is small, so constant times up. This says that the growth rate is initially close to being proportional to its size. So this is the growth rate, and this is the size right there. In other words, the relative growth rate is almost constant when the population is small. But we also want to reflect the fact that the relative growth rate decreases as the population p increases, and becomes negative if p ever exceeds its carrying capacity of capital K. The maximum population that the environment is capable of sustaining in the long run, which is the maximum population that carrying capacity. The simplest expression for the relative growth rate that incorporates these assumptions is over here, 1 over population p times by the growth rate dp over dt equals to constant K times 1 minus p over population over the carrying capacity capital K. So multiplying by p on both sides, we obtain the model for population growth known as a logistic differential equation. So dp over dt is the growth rate equals to constant times the population, and then times it by 1 minus the population over carrying capacity. So this is the one that's similar to this one right here. So this is the logistic sequence, P of n plus 1 equals to K Pn times 1 minus Pn. As opposed to here, you're dividing this by the carrying capacity over there. So yes, very, very similar. And I just wanted to go over that quick recap as well by reading this out. Okay, let's go further. So the discrete, or individually separate and distinct, that's essentially what discrete means, model with sequences instead of continuous functions is preferable for modeling insect populations where mating and death occur in a periodic fashion. All right, going further, an ecologist is interested in predicting the size of the population as time goes on and asks these questions. Will it stabilize at a limiting value? Will it change in a cyclical fashion? Or will it exhibit random behavior? So then we're asked here, and I did this all in the background. I made an Excel sheet instead. So write a program to compute the first n terms of the sequence starting with an initial population P0 or P0, where P0 is between 0 and 1. So that's the population that we're given. And it states, use this program to do the following. Task 1. We're asked calculate 20 or 30 terms of the sequence for P0 or P0 equals 1 over 2, and for two values of K such that such as K is between 1 and 3. And we're asked to graph the sequences. Do they appear to converge? Repeat for a different value of P0 between 0 and 1. And then does the limit depend on the choice of P0? And does it depend on the choice of K? And then we're given other tasks here. I'll read those ones shortly, but let's just go straight ahead to solutions to task 1 right here. Alright, so task 1 here, we're asked to calculate 20 or 30 terms of it, of P0 equals 1/2, and for two values of K between 1 and 3. So we graph the sequences. So here's what I've done. I've tabulated 20 terms of the sequence with the following values for P0 and K, and you can download my Excel sheet in the following link as well. So here's the Excel sheet there. And here's the table that I've made. So there's P0 right here and K. So these are the values. So this is the first table right here where P0 is 0.5. So that's what we're asked to start with. And then K is, I chose 1.5. So K is between 1 and 3. So here's 1.5 like that. And see what happens. It went up to 20 terms. So it starts off 0.5, the population, 0.375, then 0.35. And then 0.3415, etc. all the way. And then you can see here it's leveling off at 0.0333, at least appears to do so. And then furthermore, I changed it to, then I did another calculation here. So now we have P0 is 0.5, K is 2.5. Again, it's between between 1 and 3. As here, we're asked to repeat for a different value of this, and does the limit depend on the choice of P0, or does it depend on the choice of K? And also graph it as well. So that's what we have here. This one 0.5, and as you can see, it goes 0.5, 0.625, and then all the way goes down here to 0.999, or appears to be leveling off at 0.6, interestingly. And then changing the P0 to 0.875. Yeah, 0.875, so we've increased the initial population, but the K, if you leave K 1.5 here, what ends up happening is, well, this goes 0.875, 0.16, all the way to 0.333. That's very interesting. Yeah, so it's leveling off like that. And likewise here, 0.875, so we just changed, the, repeat for a different value of P0. And then here, made it 0.875 again. And this one's 2.5. Is K, and then you can see the K, well, this will have a 0.6 value there. So plotting this to make some sense out of it. So here I've plotted all of them together just to show what happens. So the circle is here, and this is P0 is 1.5, and K is 1. P0 is 0.5 or 1 over 2, and K is 1.5. So it's right here. So notice how this one it goes. I believe it goes like this, and it levels off there at 0.33. And then likewise here for the circle over here, if you change P0, if you change P0, then the leveling off area is still going to be 0.333 because the K is the same. So notice here goes circle from this side. But then now if you go back to the top one, K is 2.5. So this is K equals to 1.5. This is K equals to 2.5. You can see the triangles is K equals 2.5, and notice here for P0 is 7 over 8 or 0.875, same thing. And again, you can see the discrete population how it is like that. And notice here when we start off at P0 is equal to 0.875 or 7 over 8, starts off here. That's a circle and a triangle, so that's or this, depending on this value of K. And notice this one goes all the way down here for the circle, goes all the way down. Actually, it jumps over here. It jumps here, then goes like that. That's very fascinating here. Whereas this one here, the triangle goes like this and goes like that. So yes, it depends on the value of K, not the value of P0. And here I've graphed them individually just to see them a bit better. So for P0 equals to 0.5, or the initial population is 0.5, the sequence converges to about 1 over 3 for K equals 1.5, and 0.6 for K equals 2.5. So yes, it goes like this for the K is equal to 1.5, K equals 1.5, and this one's K equals to 2.5. This is the same population, starts off here, and notice the triangle, and this is the same thing there. It goes like that. So yes, it depends on It depends on the value of k. So for p naught equals 7 over 8 or 0.875, the sequence still converges to about 1/3 or 0.333 for k equals 1.5 and about 0.6 for k equals 2.5. So you start off all the way up here, the population. So this one either goes like this in a circle like that, or goes like this and goes like that for, again, k equals 2, 2.5, k equals 2, 1.5 in the circle like that. Just erase this for neatness. Going further, so the limit of the sequence seems to depend on k, but not on the initial population, p0. So now let's look at the task 2. So calculate terms of the sequence for a value of k between 3 and 3.4 and plot them. What do you notice about the behavior of the terms? And here I just used the initial population that the calculus book used in its solutions. But anyways, and it says here, what do you notice about the behavior of the terms when you increase them even higher here? So instead of going from here, which was from k is between 1 and 3, here we're looking at k is between 3 and 3.4. So increasing it has some very interesting results. So let's just keep going further here. And let's look at the solution for task 2. So we're going to change k between 3 and 3.4 and plot them. What do you notice about the behavior of the terms? So again, from the Excel sheet, and again, I recommend downloading it and playing around with it. It's pretty interesting. So plotting in the same Excel sheet from above and selecting p naught is, or the initial population is equal to 7 over 8 or 0.875 over there. K, and again, k equals to 3.2, so between 3 and 3.4. It seems that the terms of the sequence fluctuate between two values, about 0.5 and 0.8 in this case. So here is initial population of 0.875, k is 3.2, and we start off at 0.875, then goes to 0.35, so it goes like this. 0.3, then it goes to 0.728, goes up, and then it goes to 0.633 like this, and then it goes to 0.74, and then it goes to 6.1, and then it goes to 7.6, and then as you can see, it gets wider and wider. Yes, it just goes wider and wider. So from here, then it goes over to close to 0.777, and then 0.555, yeah, 0.55, and so on. It just keeps going up and up. And notice how, yeah, now it starts to level off seemingly. So yes, very, very interesting stuff here. So I'm gonna erase this. And yeah, that's just solution 3 or 2 right there. Let's just look at task 2. So there's total is going to be 4 questions. So task 3 of the project was experiment with values of k between 3.4 and 3.5. So increasing even higher, and then and states what happens to the terms. So let's go and see what happens here. So solution to task 3, experiment with values of k between 3.4 and 3.5. So for the initial population of, we'll just use 7 over 8 again, and k equals 3.42 or 3.45. So we're going to change it to just tiny bit higher than 3.4, and then 3.45 is in between. So it appears the terms eventually fluctuate between 4 values. And I'll show you that right here. So note that for the following chart for k equals 3.42, my calculus book states that the pattern persists into these 4 distinct distinct quote branches, even after 1,000 terms, which in that case the first and third terms in the pattern differ by only 2 times 10 to the power of -9, while the first and fifth terms differ by only 2 times 10 to the power of -10. So very, very, they're very, very close, but still distinct, but still a tiny bit different. And I'll show you what I mean by that. So here it looks like it's coming into 2 terms. I mean 2 values here, but it's actually 4. So this one you can see it's going up and down a tiny bit. Yes, it's actually moving up and down like that. It's so in other words, there's going to be 4 distinct branches here. This one's hard to see because the value of k just barely increased from the 3.42 there. So these 4 terms from this data set is and I'll show you with different value of k it's more obvious. So for example here it's more obvious, you can see them in 4 branches. So here these terms of this population are 0.4498. So for example here, so we have 0.875 or 7 over 8 is the initial population. K is 3.42. So initially 0.875, then goes to 0.37 like that, 374, then 0.8, and then it goes to 0.54, then goes to 0.84, then it goes to 0.44, then it goes to 0.84, then 0.45, then 0.84, and then 0.44. So instead of going to 4.5, it goes to 4.4. So there's a 4.498. I have it all the way over here. So 4.498. Then over here is a then 0.84638. That's over here. Then it goes to 0.44. Then 0.844 instead of 846. And it goes to 0.449 like that, which is just restarting. So here's 0.449 is the same as over here, or similar to that branch right there, which is 449 is just this 4.5, and it gets closer and closer, but it's still gonna be separated, and as they said, even after 1,000 terms. All right, so moving forward, so this pattern is seen more clearly when k is 3.45. So here you can notice the distinct patterns, or the distinct branches. Here is one side here, one over here, and then this one here like that, and then this one like that. And you can see that one's at 0.85, 0.46, 0.84, 0.42, and then 0.85. So 0.85 and 0.84, that's over here, 0.85 and 0.84, and this one is 0.46 and 0.42, which is bigger spread out. And interestingly, over here for initial population of 7 or 8, or 0.875, and k is 3.48, so even higher. Yeah, so going closer to this 3.5. So 3.48. The sequence fluctuates about the terms 0.395. It's over here and over here, 0.395. 0.832, so it goes to 0.395. Then you have this 0.832 here. Then it goes to 487. And then 0.869 on the top. So again, there's 4 distinct branches. Very fascinating stuff. So here you see just fluctuates about this 4 branches. And now let's look at the final question, task 4. Let's go over here, read it above here, just because it's in the same order. And this was the last task of this project. It was a brief project. Yes, and this task states for values of k, so task 4, for values of k between 3.6 and 3.4, compute and plot at least 100 terms and comment on the behavior of the sequence. And then, yes, we're even increasing it further, it's 3.6, 3.4. And then we're asked, what happens if you change the initial population by 0.001? This type of behavior is called chaotic and exhibited by insect populations under certain conditions. So very, very interesting. So we're increasing the value of k, and then we're going to be increasing just barely the population to see what happens. And again, yeah, this project is much more brief, and there isn't too much mathematics, and it's more of a... Yeah, alright, let's just see what happens here, and it's quite interesting graphs right here. So this is going from a lot of terms. I went up to 200. Just my calculus book solutions did as well, so I just followed it. So here the chart for initial population of 0.5 and k is 3.7, so we're going even higher k values, and then we'll see what happens when you increase by 0.001. So you have it like this. So here's the chart, and it shows below, and it's pretty chaotic. You have the populations going everywhere, essentially everywhere as you're getting larger and larger. So you start off with 0.5, and it goes up like this, and here the table for it is all in the Excel sheet. So, yeah, very fascinating. Just seems all chaotic. There's some patterns here, for example, and here there's just random apparent patterns, which is very interesting. So now what happens is, let's increase this by 0.001, and we get just a it's a completely different graph. There's still some patterns, but notice this one, it becomes like that. This becomes like that. This one doesn't have it there, so this one only has it there. So notice these sharp points like that. There's no sharp point here. So yeah, the graph changes completely, and it's hard to find patterns. It seems like there's some sort of pattern there, but it's just fleeting patterns. So going further, now we have P naught is 3/4 or 0.75, and then increase K to 3.9. The chart is once again changed completely by modifying P naught by 0.001. So here is over here, just so yes, here it is for initial population of 0.75. Starts off here, and it goes randomly all over the place. It's me just drawing everywhere. And K is 3.9. There's again some fleeting patterns like this, like that going down there, but nonetheless, it's hard to see. Then now when you change by minus the population by 0.001, and it's completely different. Notice there's no gap there. Now there's a giant gap there. And yeah, very, very fascinating stuff. So it completely changes. And now as k increases, the values are spread out vertically. And here as well, look at the k initially here. It's 3.9. And then this one here is 3.7. So this is higher up like that. A bigger difference from the bottom. When you increase k, it stretches out. Even here, it's stretched out more to this. This one's a bigger gap for the smaller k value. But now we're going to increase k even more. So as k increases, the values are spread out vertically with extreme values getting close to 0 and 1. Yes, notice what we have here. 0 is all the way, yes, you have some values going all the way touching it. And this is for k is equal to, yes, k equals 3.999. And population initially is 0.5. So yeah, notice here 0.5 just jumps to one of these, right away to the extremes. It's all over madness there. So there seem to be some fleeting patterns in these graphs, but on the whole, they are certainly very chaotic. So very, very fascinating stuff. So yeah, that is all for today. It was just a quick video on this project. And I'll be back to even my recently longer videos on math topics. And yeah, so this is very interesting. Hopefully you enjoyed this one. And yeah, just scrolling up here. And again, I highly recommend downloading the Excel sheet, playing around with this. Very, very fascinating stuff. And again, just playing around with this logistic sequence. And this is similar to the logistic differential equation. And all we're doing is over here. So we just take the population. So we take the initial population, times it by the k value, and then times it by 1 minus this population. Then we get a new one here, and we can get very chaotic ones for increasing values of k, which is very fascinating. Anyways, that's all for today. Hopefully you learned, and like always, you can download these exact notes in a link in the description below, as well as viewing these notes on Steemit. I'll be uploading those in article format shortly after this video. Anyways, that's all for today. Thanks for watching, and stay tuned for another Math Easy solution.